A couple of months ago, I posted this little video on my social channels about Apollo 6, and in the captions I mentioned that it was the final qualification of the Block 2 command module. Someone quickly pointed out that it was a Block 1 model and that only Apollo 7 and later missions flew the Block 2, to which I replied that Apollo 6 was actually a Block 1 with significant Block 2 elements, making it a hybrid of sorts and thus the final qualification of those elements before the Block 2 flights. And then I thought, I know way too many details about this spacecraft. So today, we are going to talk about why North American Aviation built NASA two versions of the Apollo command module. Welcome everyone, I am Amy. This is The Vintage Space, my little corner of the internet where we talk about all things mid-century with a very heavy emphasis on space exploration and space-age tech. So two versions of the Apollo command module built side by side seems a little needless and redundant, right? It kind of was, but it's not like NASA did it for funsies. It's actually a really interesting story that has everything to do with big engineering challenges and almost nothing to do with spaceflight. Before we dive into the Apollo command module, you guessed it, we are going to look at some earlier context. We have to understand some pre-Apollo decisions because they played a big part in shaping the eventual lunar spacecraft, which in turn helps us understand the command module's duplication. NASA was incepted in 1958 as a reaction to the Soviet Union launching Sputnik, the 184-pound satellite that proved the Soviets were more technologically advanced than America had thought. With space suddenly a looming battleground in the building Cold War, President Eisenhower established this new civilian space agency to bring together all America's pre-space programs under one umbrella. I've told this story in more detail in this video right here and in depth in Breaking the Chains of Gravity, so if you want that full story, check out the link in the description. Bringing together America's space programs was NASA's official raison d'etre. Unofficially, though, NASA's goal was to put an American in space before the Soviet Union launched one of their guys. Figuring out how to do that fell to the Space Task Group, the group within NASA behind the human spaceflight program. And from the STG's perspective, speed was the most important consideration. NASA and the Space Task Group had a couple of existing programs to choose from, foremost among them the X-15 program. The X-15 was a missile-looking spaceplane that air-launched from under the wing of a B-52 bomber. Once free, the pilot ignited his rocket engine and, depending on the mission profile, reached speeds upward of Mach 6 or altitudes in excess of 300,000 feet, where he controlled the plane with reaction controls. The flight ended with an unpowered landing on the dry lakebed at Edwards Air Force Base. It wasn't a stretch for the X-15 design team from North American Aviation to see that an additional fuel tank could turn this suborbital spaceplane into an orbiting vehicle. But whatever designers promised about an orbital X-15 version, the STG felt the technology just wasn't quite up to the task of a real human spaceflight. They turned instead to an alternate vehicle that emerged as an offshoot from nuclear missile research. Max Faget, an engineer with NASA's Langley Research Center, had spent years working on how to ensure a nuclear warhead detonated on its earthly target and not from the heat of atmospheric friction as it fell to that target. He found that a blunt, round-bottomed casing offered natural protection. This shape created a cushion of air that spared the warhead the worst of the re-entry heat. The same would be true of a spacecraft returning from orbit. It was a crude but effective solution that quickly gained traction within NASA as the fastest way forward for the inaugural Mercury program. Around the time NASA introduced its first class of astronauts to the world, it was committed to getting one of them into orbit in a blunt, round-bottomed, capsule-style spacecraft. But some within the agency were looking ahead at more distant, long-term goals, like a possible lunar landing. A series of meetings were held over the course of 1959 as part of the Advanced Manned Spaceflight Program, and since NASA was devoted to the blunt capsule for Mercury, preliminary lunar mission planning centered around the same blunt capsule going to the moon. It seemed perfectly feasible at the time. Where the spacecraft was concerned, it would still need protection when falling through the atmosphere, and in fact, it would need better protection at lunar re-entry speeds than orbital re-entry speeds. With the capsule-style spacecraft assumed to be a given, the other half of the equation was simply a massive rocket to launch it on a path directly to the moon, where it would land before launching back from the surface on a path straight for Earth. There's a trend here. Prevalent thinking at the time was the simplest way was best. Much like how the blunt capsule simplified the orbital mission, the thinking was that going straight to the moon would be the easiest way to get there, and that landing that spacecraft upright ready to launch again was the best way to actually make a landing. There's some logic there. Fewer moving parts means fewer things to go wrong. Not to mention this was the vision of space exploration portrayed in the media, from pulp fiction novels to the now iconic Chesley Bonestell paintings. Unfortunately, the seemingly simple method was technologically really difficult. The question of how to go to the moon is properly called the mission mode decision, and the path of going straight from a launch pad on Earth to a landing on the moon is a mode called direct ascent. The challenge in direct ascent is that it's really heavy. A spacecraft that needs to land on the moon and also take off from the moon and fly straight back to Earth needs a lot of propellant. These are two very fuel-heavy mission stages. That means the payload leaving the Earth in the first place is pretty heavy because of the mass of all of that fuel needed to get it back off the moon. So to get that heavy spacecraft off the Earth in the first place, you need a rocket powerful enough to lift all of that mass. Early lunar mission planning identified this problem and came up with a solution, the NOVA rocket, an absolute behemoth of a launch vehicle that could produce 12 million pounds of thrust at launch. Or at least it could on paper. In 1959, it was all theoretical. In reality, the Redstone, slated to launch the first Mercury missions, couldn't launch even that spacecraft into orbit. Developing NOVA was already identified as a significant piece of the lunar mission puzzle, effectively the pacing item. If the rocket development ran into trouble, it could seriously delay the entire program. So NASA came up with an alternative mission mode that would enable the same lunar mission without NOVA, Earth Orbit Rendezvous. This mode called for launching the big lunar spacecraft in two pieces on two smaller Saturn-class rockets, then assembling it in Earth orbit before launching the whole thing to the moon. These smaller Saturn rockets were still massive, but more likely to come to fruition. At the time in 1959, Wernher von Braun and his team of rocket engineers were developing missiles for the US Army, one of which, the Redstone, was being man-rated for Mercury missions. A Redstone variant, called Jupiter, was mainly used as a sounding rocket for spacecraft and satellite launches. The next rocket the team was developing after Jupiter was called Saturn, so named because Saturn is the next planet after Jupiter. The Saturn family was a larger rocket with multiple iterations. The Saturn C3 was a three-stage rocket whose C1 first stage was powered by Air Force-designed F1 engines, an S2 second stage powered by J2 engines built by North American Aviation's Rocketdyne division, and an S4 third stage powered by Douglas Aircraft-built RL-10 engines. The C4 version was identical to the C3, but with a more powerful third stage, an uprated S4 called the S4B. An even larger version, the C5, added a fifth F1 engine to the rocket's first stage for even more power at liftoff. That C5 was powerful enough to launch the two parts of the lunar spacecraft that could then be assembled in Earth orbit. But all this planning was theoretical. The real mission was far in the future. On December 16, 1959, the lunar mission was officially incorporated into the Space Task Group's long-range plan schedule for, quote, 1970 and beyond. Still, managers and engineers were discussing it, and weeks later, the mission hit an important landmark. Over lunch one day in January of 1960, Abe Silverstein, director of NASA's Office of Spaceflight Programs, casually used the name Apollo in reference to the lunar mission. He thought the image of a god driving a chariot across the sun was appropriately grand for what they were planning, and the name stuck. Bits and pieces of Apollo fell into place in the weeks that followed. A three-man crew, because it was assumed to be all male at the time, was selected to prevent deadlocked decisions and give the option of having one person awake in the spacecraft at all times. A shirt-sleeves environment was chosen for safety and comfort, and NASA wanted to explore both land and sea options for touchdown at the end of the flight. The mission on the whole was loosely broken into 6 stages. The first 3 stages were just the rocket firing in sequence to get the spacecraft off the launch pad and into Earth orbit. The 4th stage would propel the spacecraft to the moon. The 5th stage would slow the spacecraft for a soft lunar landing. The 6th stage would launch astronauts from the moon's surface and send them back home. The program as a whole was similarly divided into two phases, an Earth orbital phase for testing and a lunar phase for the actual landings. Apollo was officially put on the books on July 5th of 1960, after the House Committee on Science and Astronautics formally recommended that the lunar landing be NASA's next goal in a new high-priority spaceflight program. This meant development on the spacecraft could begin in earnest. In the second week of September, the agency released a formal request for proposals, and on October 25th, awarded General Electric, Convair, and the Martin Company study contracts. Basic guidelines included crew size and the spacecraft's blunt shape, but it didn't say anything about the mission mode. NASA was still assuming direct descent would be the best way forward, but it hadn't yet ruled out Earth orbit rendezvous. General Electric, Convair, and the Martin Company were all stymied by NASA's indecision. All three said that without a firm mode, they couldn't design the spacecraft. Amazingly, even with that industry response, some people within NASA felt it was better to put off the mode decision and keep options open. Around the same time, a fourth contractor, Grumman Aerospace, started an independent study into the lunar mission. Grumman engineers, like those at NASA, saw the mass of the lunar spacecraft as the big problem, and wondered if it wouldn't make more sense to not land the whole thing on the moon, but instead touch down with a smaller, dedicated craft. It would be complicated, but the payload launching from Earth would be lighter, so the trade-off was net positive for the mission. When John F. Kennedy took office in January of 1961, neither the United States nor the Soviet Union had taken any big steps in space, but that changed within months. On April 12, 1961, Yuri Gagarin became the first human to orbit the Earth. It was a blow to the Kennedy administration, and days later he was dealt another with the failed invasion of the Bay of Pigs. Kennedy needed a win, so he looked to space. I have a video that goes into detail about this decision, but in short, on Kennedy's request, Vice President Lyndon Johnson met with NASA brass, who confirmed that the moon was a doable mission within the decade, feasible as early as 1967 if personnel and funding were transferred to the program immediately, though fast-tracking it came with a trade-off of sorts. NASA Associate Administrator Robert Siemens warned that fast-tracking Apollo would turn it into a crash program. It wouldn't be long-term architecture that NASA could use for decades to come. Rather, it would be technology that would more than likely become obsolete at the end of the lunar program. The political need weighed heavier than any technical considerations, and LBJ passed the recommendation on to Kennedy, who somewhat grudgingly agreed. The president famously called for an American mission to land a man on the moon and return him to the Earth within the decade on May 25, 1961. Kennedy's call to action turned Apollo from back-burner distant plan to NASA's technological focus, but that didn't mean the agency suddenly had a clear game plan. Having a time frame didn't answer the question of what mode the mission should take. So still without a mission mode decision, but with direct descent as the forerunner, NASA pressed forward with other aspects of Apollo, specifically the spacecraft. On July 28, 1961, the agency requested bids from 14 aerospace companies, each hoping to build America's moonship: Boeing Aerospace, Chansavat, Douglas Aircraft, General Dynamics/Convair, General Electric, Goodyear Aircraft, Grumman, Lockheed Missile and Space Company, McDonnell, Martin Aircraft, North American Aviation, Radio Corporation of America, Republic Aviation, and Space Technology Laboratories. Each contractor was instructed to submit its bid to NASA, a bid that included a 3-phase hardware testing program in Earth and lunar orbits, as well as its plan to seamlessly incorporate changes into the vehicle over the course of its development lifetime. Interestingly, these contractor bids were not asked to include a design for the actual lunar landing spacecraft. NASA was asking only for bids to build the core or command module of the Apollo stack, the main vehicle that would support the crew for 2 weeks and bring them home safely. So it was never expressly stated that this spacecraft would be landing on the moon. The contractors assumed that a simple landing stage would turn their mothership into the lunar landing vehicle. And at this point, contractors were also assuming their vehicle would launch in one piece, but were asked to outline in their proposals how the spacecraft could be modified for a rendezvous mission in case the mode decision changed. They were also asked to outline a potential lunar landing laboratory that could descend to the surface while the mothership stayed in orbit around the moon. The hopeful contractors had questions. During a meeting at Langley Field in Virginia on August 14th, representatives from these companies posed more than 400 questions to NASA about the Apollo spacecraft, each of which agency representatives answered with the most recent information it had on hand. But all in all, there were a lot of unknowns. In the end, only 5 bids for the Apollo spacecraft were presented to NASA on October 11, 1961, and they all went straight to an 11-person board appointed by Robert Siemens that brought together members of the Space Task Group, the Marshall Space Flight Center, and NASA headquarters in Washington. 3 bids came from companies who had teamed up in an effort to increase their odds of winning. 1 bid came from General Dynamics/Astronautics in conjunction with the Avco Corporation. A second bid came from the General Electric Company working with the Douglas Aircraft Company, the Grumman Aircraft Engineering Corporation, and Space Technologies Laboratories. A third bid came from the McDonnell Aircraft Corporation, the contractor behind the Mercury spacecraft, now partnered with the Lockheed Aircraft Corporation, the Hughes Aircraft Company, and the Chance Vought Corporation. Only the Martin Company and North American Aviation submitted their own bids. As an important sidebar, it's worth noting that a month earlier, on September 11th, North America had won the bid to build the S-2 second stage of the Saturn V rocket. Few thought the company stood a chance of winning a second major Apollo contract. After 2 months of deliberation wherein the board considered the technical approach, qualification, and overall business model of each bid, Martin was the winner with 6.9 points out of 10. General Dynamics and North American tied for second place, each with 6.6 points. General Electric and McDonnell tied for third place with a score of 6.4. But another informal criteria of experience pushed North American into the lead. The company had a reputation for building exceptional aircraft such as the P-51 Mustang and the B-25 bomber, and was also the visionary builder behind the X-15 aircraft. On November 28, 1961, NASA announced that North American would be building the Apollo Command Module. North American had won the bid, but NASA was still stuck on the mission mode decision. Towards the end of 1961, the agency was starting to favor Earth orbit rendezvous, but another mode was gaining traction: lunar orbit rendezvous. This was the method Grumman had looked into a year previously, and now NASA engineer John Hubble, assistant chief of the Dynamic Loads Division at NASA's Langley Research Center, had seen the same thing Grumman had. He realized that the whole mission would be lighter and therefore simpler to launch if the entire stack was modular. It could launch on a single Saturn-class rocket, then, once at the moon, leave the heaviest part of the payload, the fuel for the return journey, in orbit and land instead with a dedicated landing vehicle. To leave the moon, the crew could use the lunar lander's descent stage as the launch pad for the ascent stage. The ascent stage alone would rendezvous with the waiting mothership in orbit. The now unneeded ascent stage would be jettisoned before leaving lunar orbit, meaning only the lightest payload of the command module would return to Earth. Hubble's research consistently showed lunar orbit rendezvous was the only viable option for Apollo because of how it managed the spacecraft's mass over the course of the mission. The challenge was doing the rendezvous in the totally unknown lunar environment. Undaunted, he wrote his proposal in a letter to Robert Siemens, wherein he somewhat famously acknowledged his unorthodox position to be akin to a voice in the wilderness. NASA seriously looked into lunar orbit rendezvous in early 1962, and it quickly became the frontrunner. By spring, the Space Task Group and the Manned Spacecraft Center in Houston were firmly behind this mission mode, much to the chagrin of engineers at the Marshall Space Flight Center, the site where Wernher von Braun's former Army team was now building rockets for NASA. Von Braun and his team knew that Earth orbit rendezvous would give them a reason to develop a larger number of advanced boosters, something that would feed nicely into their future goal of assembling a space station in Earth orbit. From their perspective, Earth orbit rendezvous was the best chance to have Apollo not be a dead-end program, but instead to have some elements feed into the next generation of space exploration, bringing them long-term job stability at the same time. For the moment, though, future mission considerations weren't nearly as important as the need to make it to the moon by the end of the decade. To give lunar orbit rendezvous a fair shot, von Braun studied the method himself and was forced to concede that it was indeed the only way Apollo would make it on time. With all the key people in agreement, NASA announced it would be going to the moon with Lunar Orbit Rendezvous on July 11, 1962, though it was retaining Earth Orbit Rendezvous and Direct Descent with NOVA as backup modes. They were backup modes until NASA firmly committed to LOR on October 11, 1962. October 11th, 1962. That's nearly a year after NASA awarded North American the contract to build the Apollo spacecraft. So this means the contractor had a year of work on the vehicle under its belt when, all of a sudden, it wasn't landing on the moon. It was building the mothership from which the lunar lander would be descending to the surface. And what was more, North American didn't win the bid to build the lunar module. That contract was awarded to the Grumman Aircraft Engineering Corporation on November 7th of 1962. NASA's late mode decision risked undoing a full year of work at North American, so the contractor searched for a way to save it. North American's Apollo Command Module suddenly no longer fit into the lunar mission profile, but it would be up to North American to somehow make it compatible with the lunar lander being built by Grumman. And again, NASA didn't have much by way of guidance for its contractor. NASA sent a somewhat vague contract change notice outlining constraints for different ways the command and lunar modules could line up for docking. The space agency didn't totally care how it happened. It just had to be a method that would work after the upper stage of the Saturn V, the S-4B, fired to send the whole stack on a path towards the moon, and transfer between the two vehicles had to be some kind of pressurized tunnel so the astronauts wouldn't need to suit up. At this point, NASA also ordered that this new lunar mission-capable command module have a hatch that could be open in flight for spacewalks or EVAs. The request for a docking system and the new hatch were foremost on a sizable list of changes NASA sent North American towards the end of 1962, and they were substantial enough changes that North American was now, in essence, building two versions of the same spacecraft simultaneously. Since both had the same basic structure and systems, the contractor came up with a solution to avoid throwing away all its past work: a block concept. The original iteration of the command module was now designated Block 1. This version wouldn't have a crew hatch that could open easily, nor would it have the docking ring, so it couldn't support lunar missions. But since it was fairly far along in its development, North American decided it would be a viable testbed for basic spacecraft elements like hardware and heat shield. The advanced spacecraft, the version with the easy-to-open hatch and docking ring, was the Block 2 version, built in parallel with the Block 1 to keep Apollo on track. North American presented the block concept to NASA, and the space agency signed off on it on January 24, 1964. It didn't sign off on the spacecraft's general layout until September of 1964. The hatch was one of the biggest differences between the two blocks. The Block 2 hatch used a larger mechanism to overcome thermal warping issues and some additional hardware to secure it when it was open in flight. But that wasn't the only change that became a point of contention between NASA and North American. Another significant difference between the blocks was the layout of materials inside the crew cabin over concerns of a fire, and this had been a sticking point between NASA and North American for a while. NASA's original 1961 request for proposals had called for the Apollo spacecraft to use an oxygen-nitrogen mixed gas system to give the crew an atmosphere similar to what we breathe on Earth. That was the cabin environment North American had included in its winning bid and set off developing that system. But a year later, NASA had changed its mind. Tanks to hold two gases and the hardware to deliver it to the crew cabin all added mass, and the system to manage the balance of gases was challenging to say the least. If it failed, the crew could be killed before they even realized there was a problem. A pure oxygen system would be lighter and simpler, needing just a common pressure sensor to ensure the cabin was adequately pressurized. NASA thus reversed its initial decision, changing the crew cabin from a mixed gas to a pure oxygen environment. North American was not in favor of the change. Designers felt the simplicity of a single gas system didn't outweigh the danger it posed to the crew. In a pure oxygen environment, a single spark could turn into a raging fire. NASA countered that the risk of a fire was minimal because it was a low-pressure environment. The spacecraft would be pressurized to just 5 pounds per square inch in flight, which wasn't enough to support a fire the crew couldn't manage. Besides, NASA had used pure oxygen in both Mercury and Gemini missions, so why change something that wasn't problematic? The switch from a dual to single gas environment came via a formal contract change notice on August 28, 1962. Almost 4 years later, on April 28, 1966, a fire broke out during an unmanned test of the Apollo Environmental Control System. No one was injured, but some spacecraft hardware was destroyed. The incident, interestingly, didn't reopen a discussion over the crew cabin environment. The damage was attributed to a commercial-grade strip heater that wouldn't be present on a lunar mission. The fire did, however, bring changes to the crew cabin layout. A full survey was done to ensure no combustible material was too close to any electrical systems. North American also did a full survey to eliminate potential fire hazards from fluid leaks, overheating lamps, or large areas of exposed fabric and foam. The changes, though, were only made to the Block 2 spacecraft. No changes were made to the Block 1 because it was nearing its initial flight. As Apollo came closer to flying, NASA split its Apollo launches into phases to best take advantage of the 2 blocks coming off the assembly line at North American. Before we proceed, a super quick note on nomenclature. Missions with an A designation stand for Apollo and are just tests of Apollo hardware. SA stands for Saturn Apollo, denoting a test that's primarily for the rocket, whereas AS, standing for Apollo Saturn, was a test focusing on spacecraft systems and development. The first flights were launch abort tests using boilerplate models. Missions A001, A002, and A003 were all launched on Little Joe rockets from the White Sands Missile Range in New Mexico. A004, a test flight with a Block 1 spacecraft, was the 5th and final Little Joe 2 flight on January 20, 1966. After these Little Joe flights, NASA moved on to full Block 1 tests. SA-201 launched spacecraft 9 as its payload and was the first Saturn 1B test. The Saturn 1B was the former Saturn C4 rocket. Launched on February 26, 1966, this was a test of every aspect of a launch, from hardware, rocket staging, electrical subsystems, and the mission support facilities NASA put in place to support Apollo missions, as well as the third-generation instrument unit, which is effectively the Saturn V's brain that guided it in flight. AS-203 had no command module on board when it launched on July 5, 1966. It was predominantly a test of the S-4B's orbital relight capability. In September of 1965, the next Block 1, Spacecraft 12, was shipped to NASA, and in early 1966 was assigned to the next mission in the series, AS-204, though the crew preferred to call it Apollo 1. It was exactly the kind of flight North American had envisioned when it had pitched the block concept to NASA 2 years earlier. Apollo 1 would launch on a Saturn 1B rocket for an Earth orbital shakedown flight, a mission designed to test all the spacecraft's hardware, systems, and subsystems in the relative safety of Earth orbit. The crew of Gus Grissom, Ed White, and Roger Chaffee found their vehicle was fraught with problems. When it arrived at the Cape, NASA immediately identified 113 outstanding engineering orders and soon added 623 to the list. The space agency and the contractor addressed the most pressing issues as pre-flight checkout tests continued. Spacecraft 12 was mated to its service module in September of 1966, and the first combined system tests were completed within weeks. On October 7th, Spacecraft 12 was certified as flight-worthy, though this status was conditional pending resolution of outstanding technical problems that continued to dog pre-flight qualification tests. Ongoing spacecraft changes took their toll on the crew. The astronauts were struggling to keep up with changes while training in simulators that didn't always reflect the latest updates to the flight vehicle. Ongoing tests revealed shoddy repairs. Technicians found failures in the communication system on account of broken wires, bent pins, and faulty connectors. Repairs to one issue often introduced new weak points into the whole system. A month before the scheduled launch date of February 21st, the spacecraft's cable assemblies were deemed unacceptable and the communication system unsafe for human flight. NASA pressed on in spite of these issues and knowing full well that the Block 1 shakedown only had some relevance to eventual lunar missions. Apollo 1 was testing out a spacecraft that had minimal importance for the program. There wasn't much overlap between this version and the one that would fly to the moon. On January 27th, it was time for the Plugs Out test, a test NASA had been running since the Mercury days. This was a full, simulated launch with the spacecraft running on its own power. Everything was exactly as it would be during a real launch, including the cabin pressurized with more than 16 pounds per square inch of pure oxygen. This created the equivalent pressure differential as a spacecraft would have at 5 psi against the vacuum of space. The test was plagued with problems, from a strange smell of sour buttermilk in the oxygen feed system to communications problems leading to hold after hold after hold. At 6:31 p.m. in Florida, technicians in Mission Control saw a sudden rise in oxygen flowing into the crew's suits and telemetry suggesting one of the astronauts was moving around in his couch. 4 seconds later, controllers in the firing room and in Mission Control heard the word fire over the communications loop. Then a fire in the cockpit and a bad fire. In the blockhouse, engineers and technicians turned to the television monitors showing a live picture of the spacecraft and saw flames through the porthole window. Technicians rushed to open the hatch, but the spacecraft's hull ruptured, sending flames pouring out into the White Room. Gradually, the oxygen dissipated, starving the fire, but by the time technicians could reach the hatch and wrestle it open, all 3 astronauts had been killed by the toxic smoke that had seeped into their oxygen supply. The Apollo 201 Review Board was created within hours to determine the source of the fire and make sure it never happened again. The dim silver lining was that the vehicle was on the launch pad, easily accessible and ready to tell its story. Technicians disassembled spacecraft 12 piece by piece, mashing it against another Block 1 spacecraft, spacecraft 14, as they went. The disassembly showed discrepancies and shoddy workmanship in spacecraft 12, revealed that constant removal and reinstallation of systems and wires had left bunches exposed and frayed. There was evidence of a fluid leak in the coolant system. There was also the procedural issue that electrical connections had been disconnected while they were powered. And of course, none of the changes North American made to reduce flammable materials in the spacecraft after the 1966 fire had been incorporated into the Block 1. Another major problem was that the Plugs Out test had never been classified as hazardous, so appropriate emergency equipment hadn't been on hand. The hatch was another serious issue. The Block 1 hatch was a complicated tripartite design. It had a lightweight removable inner structure hatch and an outward opening heat shield hatch, and the boost protective cover hatch. To open it, the crew had to equalize the pressure across the inner structure hatch, then unlatch and remove it, stowing it inside the command module. Next, they had to strike a plunger to open the boost protective cover hatch. With 2 hatches out of the way, the last step was to unlatch the heat shield hatch and push it outward, opening the boost protective cover hatch at the same time. The only reason this complicated design had been approved for the Block 1 was because it wasn't going to open in flight. This hatch was only designed to open at the end of a mission, once the spacecraft was safely on the recovery carrier. Under normal circumstances, it took 90 seconds. But the fire hadn't been normal. As the pressure rose inside the cabin, the crew stood no chance to equalize the pressure and remove the inner hatches, and technicians in the White Room were similarly powerless against the high pressure. At the end of the day, one of the biggest problems was management. The review board found that the various program branches weren't always up to speed on the latest hardware changes or even spacecraft status. Requested changes were made but not acknowledged, a communications breakdown that had allowed for non-certified equipment to be installed in spacecraft 12. The board impressed upon NASA the need for better communication between departments and contractor to ensure maximum clarification and understanding of the responsibility of all the organizations involved, with the goal of building a coordinated and efficient program. The board also made a series of comments and recommendations regarding spacecraft hardware, but by far the biggest changes ordered after the fire affected the hatch and the spacecraft cabin atmosphere, the 2 things that were the biggest difference between the Block 1 and Block 2 models. Now, NASA and North American would have to reconsider the Block 2 hatch and the crew egress procedures and reopen the question of a pure gas environment. NASA's whole approach to the Apollo program was called into question too, specifically the decision to use the different block versions for command module testing. The Mercury and Gemini programs had progressed smoothly, in part because launches were scrubbed and missions rescheduled whenever problems arose. As such, every mission flew only when it was ready, and NASA was able to achieve new objectives with every flight. But Apollo was marked by frantic urgency, as evidenced by the decision to push forward with the Block 1 Apollo 1 mission in spite of known issues. No one would argue that testing a new spacecraft in Earth orbit before going to the moon was necessary, but in retrospect, it was downright foolish to have pushed for a mission with a non-lunar capable spacecraft. The accident investigation led to a laundry list of changes to both the Block 2 spacecraft and the Apollo program as a whole. Going forward, no manned missions would fly a Block 1 model. They would all fly lunar-capable Block 2s. And it would have some changes, most significantly the removal of lots of potentially flammable material and a new hatch. The Block 2 would now have a simpler two-part integrated hatch. The inner and outer hatches were combined into a single outward opening unit, with the boost protective cover hatch remaining a separate piece but linked to the inner hatch. Rather than the 90 seconds it took to open the original hatch, this one could be opened in 7 seconds by a pad safety officer or 10 seconds by an astronaut inside the spacecraft. There was also a change made to the cabin environment. It was too late to change to a dual gas system, so NASA and North American came up with the acceptable solution of changing the cabin environment at launch. On the pad, when the pressure was highest, the environment would be a mix of oxygen and nitrogen, and that mix would bleed out during ascent to orbit, replaced with pure oxygen. Once the crew, who would be breathing pure oxygen from their own systems during ascent, took off their helmets, the cabin would be a safe 5 psi of pure oxygen, the same as to what their bodies would be accustomed to. Testing resumed after the fire with a handful of unmanned flights that made use of the final Block 1 spacecraft. Spacecraft 17, a modified Block 1 model retrofitted with a simulated unified crew hatch and a Block 2 heat shield, launched as the payload of Apollo 4 on November 9, 1967, a mission that also saw the first all-up testing of a Saturn V. Apollo 6 was a near repeat of Apollo 4's mission with another modified Block 1 as the payload, Spacecraft 20. This flight had the full Block 2 integrated hatch installed, and the mission was primarily one to test compatibility between the spacecraft and rocket, with particular attention paid to structural activity. It launched on April 4, 1968. Spacecraft 101, the first full Block 2 with all changes made, was delivered to the Kennedy Space Center on May 30, 1968, and the receiving inspection found fewer discrepancies than any other model. It was deemed flightworthy and mated to its Saturn 1B launch vehicle on August 9th. By mid-September, 41 specific items relating to safety of the 137 action items on the spacecraft had been addressed. NASA triumphantly returned to manned missions with Apollo 7 on October 11, 1968. I originally got into the weeds on this topic years ago when I wrote an historical context section as part of Apollo Pilot, Don Isley's posthumous memoirs edited by my good friend Francis French. Isley was command module pilot on Apollo 7, so that context was a deep look at the development of the spacecraft that was then cut from the book. Nevertheless, a truncated piece is still in there, and not to mention it's a fascinating Apollo-era memoir from one of the lesser-known astronauts. I've got a link in the description if you would like to check out the book. And of course, I've also got links to my own 2 books, Breaking the Chains of Gravity and Fighting for Space, my latest dual biography of Jackie Cochran and Jerry Cobb that traces both women's careers that come to a head over the issue of women in space in the 1960s. That's going to do it from me for today. Definitely subscribe if you want to never miss a future episode. And I want to say a special shout out to all my Patreons and YouTube members for helping make the Vintage Space possible. If you want to help keep these videos coming and get access to my Discord server, there are some links in the description to help you out. And of course, links to all of my socials. Thank you guys so much for hanging out with me today, and I'll see you next time.